Look at the first quadrant of R2. That's every vector where both x and y are non-negative. Pick any two vectors in this region. For example, take the vector 1, 2 and the vector 3, 1. Add them together and you get 4, 3, which is still inside the first quadrant. So it looks like a perfectly valid vector space, but it's not. It fails one critical test. By the end of this video, you'll know exactly why, and you'll be able to identify every subspace of R2 and R3. Here's what makes something a vector space. A vector space is a set of vectors that is closed under two operations, addition and scalar multiplication. Closed under addition means if you take any two vectors, u and v in the set, their sum u plus v stays in the set. Closed under scalar multiplication means if you take any vector u and multiply it by any real number c, the product c times u stays in the set. Now we can combine these into one powerful requirement. The space must be closed under all linear combinations. A linear combination is an expression like c times u plus d times v, where c and d are any real scalars. If u and v are in the space, then c times u plus d times v must also be in the space for every choice of c and d. Nothing escapes. Let's look at the main examples. The Rn spaces, R1 is the number line, R2 is the full plane. R3 is all of three-dimensional space, and in general, Rn is the set of all vectors with n real number components. Here's a common trap. The vector 3, 2, 0, right? You might think it belongs to R2 since the last component is 0. But it doesn't. It belongs to R3. Count the components. There are 3 of them. The 0 sitting in the third position doesn't remove a dimension. Membership in Rn depends on how many entries a vector has, not on what their values are. Let's compare side by side. On the left, the vector 3, 2 lives in R2. It's a point on a flat plane with just 2 components. On the right, the vector 3, 2, 0 lives in R3. It sits on the xy plane within three-dimensional space, but it still has 3 components. Right? Same x and y values, but these are different vectors living in different spaces. Notice that 0 in the third component, it still counts. A big not equal sign sits between them to emphasize these are not the same vector. The key takeaway: 3 components means R3, regardless of whether any entries are 0. A key consequence of closure: the 0 vector must belong to every vector space. This isn't a separate axiom. It follows directly from closure under scalar multiplication. Here's the argument. Let V be a vector space and take any vector V in the space. Now multiply by the scalar 0. 0 times V equals the 0 vector. And by closure under scalar multiplication, that result must remain in the space. So the 0 vector is automatically present in every vector space. Right? This gives us the fastest disqualification test in all of linear algebra. If a set doesn't contain the 0 vector, stop right there. It's not a vector space. Don't bother testing addition. Don't bother testing scalar multiplication. Check for the 0 vector first. It takes seconds and eliminates many candidates instantly. Remember, 0 times V equals the 0 vector, and that 0 vector must be in V. Back to our opening example, the first quadrant Q contains all vectors x, y, where x and y are both at least 0. Let's test addition first. Take the vectors 1, 2, and 3, 1. Their sum is 1 plus 3, 2 plus 1, which gives 4, 3. Both components are non-negative, so the sum stays in Q. Addition passes the closure test. Now let's test scalar multiplication. Take the vector 1, 1, which is in Q, and multiply it by negative 1. Negative 1 times 1, 1 equals negative 1, negative 1. That vector lands in the third quadrant, completely outside Q. So scalar multiplication fails the closure test. The first quadrant is closed under addition, but not under scalar multiplication. you need both closures to have a vector space. 1 out of 2 is not enough. Q is not a vector space. Another failure case, consider the line y equals x plus 1 in R2. We start with the zero vector test. Is the origin on this line? Plug in x equals 0 and y equals 0. Does 0 equal 0 plus 1? 0 does not equal 1. The zero vector is missing from this line, so it is not a subspace. We could stop right here. But let's also check closure under addition to see another failure. Take 2 points that are on the line, the point 0, 1, and the point 1, 2. Add them component-wise. 0 plus 1 is 1, and 1 plus 2 is 3. So the sum is the point 1, 3. Is 1, 3 on the line, y equals x plus 1? Check. Does 3 equal 1 plus 1? 3 does not equal 2. So addition fails as well. The key takeaway is that only lines through the origin can be subspaces. Now let's catalog what does qualify. Every subspace of R2 falls into exactly one of 3 types. First, the set containing only the zero vector, just the origin, a single point. Second, any line through the origin, tilted at any angle you like. As long as it passes through the origin, it's a valid subspace. Third, all of R2 itself, the entire plane. That's the complete list. Nothing else, no curves, no half planes, no quadrants, only flat objects passing through the origin. And for contrast, remember that a line like y equals x plus 1, which does not pass through the origin, is not a subspace. Now let's move up to R3, where one new type of subspace appears. The complete list has 4 entries. First, the zero vector alone, just the origin, a single point. Second, any lines through the origin, just as we had in R2. Third, and this is the new one, any plane through the origin. This is a flat 2-dimensional surface that passes through the origin. Fourth, all of R3 itself, and that's it. Those are the only possibilities. Notice the pattern. Every subspace is flat, a point, a line, a plane, or the full space, and every single one passes through the origin. No cones, no spheres, no curved surfaces qualify as subspaces. Flatness and passing through the origin, those are the geometric signatures of a subspace. As a counterexample, consider a plane that misses the origin. Even though it's flat, it is not a subspace because it fails to contain the zero vector. Let's wrap up with 3 key takeaways. First, closure. A vector space must be closed under all linear combinations. That means both addition and scalar multiplication. If either one fails, it's not a vector space. Second, the zero vector is non-negotiable. This actually follows from closure itself. 0 times any vector equals the zero vector, so the zero vector must be in the space. Use this as your fastest screening test. Third, subspaces must pass through the origin. In R2, the subspaces are just the origin, lines through the origin, and all of R2 itself. R3 adds planes through the origin to the list. These structures appear throughout linear algebra: column spaces, null spaces, eigenspaces. They are all subspaces. The closure test and zero vector check are tools you'll use constantly. Here's the quick test. Does the set contain 0? If the answer is no, then it's not a subspace, and you're done. Next up, we'll build subspaces using span and basis.